Alright, time for another draft physics video presentation. DraftScience here on YouTube. So, continuing this conversation about the rather famous formula, used all over the place, and how could it possibly be wrong? How could it be just completely wrong? Not a little bit wrong, but completely wrong, like always gives you the wrong answer. Like barely ever gives you the right answer. Sort of like the two-slit experiment, okay? And the funny part is the history kind of shows that this is another Young. Young has his fingers on this bad equation. So just like we have Young's fingers on this nonsense that two waves create the double-slit experiment, when two waves can't explain the actual experiment, just can't happen. It's impossible for two waves to be maneuvered in such a way to make the complex two patterns of the envelope pattern and the on-off pattern. Here's another example. It's just kind of ironic. I didn't realize, and it's kind of funny. So Kathy does physics and videos. No, loves. That's it. Yeah, she loves them. Physics and history. She makes good videos, good research, all of that kind of stuff. Hard to complain. But in a sense, this clip kind of just shows how bad the history is, in the sense of how bad the reasoning was and the atmosphere of the reasoning. And, so we'll play this bit of a portrayal of the history. And I'll just point out what needs to be pointed out and such.
One of the definitive experiments.
Crap, volume. Alright, well, I'm not going to pause, so I'll just try to increase the in total volume and hope that fixes it.
Convinced Emily du Châtelet.
Crap. Yeah, so I have to fix it this way, which will make a mess. But that's okay. A little bit of a mess, no big deal. You'll survive it. Alright, so this we're going to get to later. This video is, now I have to remember where the hell it was. Forward over this way. It was somewhere around here. Yeah, that's it. Oh, great. It doesn't show up. There it is. Alright, now volume. Volume is over here. Yeah, okay. Alright, that should fix that. But now when I close this, I have to go grab this again, which is kind of silly, but that's what you have to do. So, sorry. Slight technical issue.
The damage of a moving object depended on the speed squared times the mass, or the living force, is dramatized by the 2005 documentary.
Okay, so she said, the damage done, right? Which is kind of a funny thing to say. So she didn't say the kinetic energy of, okay, is measured through this formula. So the energy of. So, it's kind of funny that she did qualify the language she used, but the language isn't qualified in any of the arguments being made in physics videos, as I pointed out with the Physics Girl video, where she concedes the momentum is the same. No losses to anything. Same momentum. You can't have the same momentum and say some energy was lost somewhere. It's not possible to have the same momentum and say there was a loss somewhere. Momentum's a vector. It has a length. If there were losses somewhere, the length of the vector has to be used to make the losses. You have to cut the momentum vector down, okay, for all the losses. So if there's any heat, well, that's part of the vector. If there's any stuff moving in another direction, sideways or something, well, you have to shorten the vector. Some steel splits in half, you have to shorten the vector. Some electricity, you have to shorten the vector. So no matter what you create, you have to short the momentum vector. Is the only place you can get the energy from. So just understand how overtly wrong and impossible it is to say the momentum stayed the same, but it lost half its energy. You can't say it and be sensible. Okay. Now, if you want to talk about how much damage things do, that's a whole different subject, right? How much damage a bullet does versus something going much slower that's much heavier, right? And so I can go all the way to like the slowness of a building moving in the wind, and you're leaning against it. Just as much energy is pushing against you as the bullet would push going through your head. But clearly the damage it can do is a lot different. So it just has to do with the application of energy, not the existence of it. You can't mess those two things up, or you don't really have rational physics anymore.
Einstein's big idea.
Graafsound in Leiden has been dropping lead balls into a pan of clay.
Dropping lead balls into clay? How very imaginative.
So this is the guy who did the Leyden jar, right? Is the one who was dropping balls into clay. Now, clay isn't very good at measuring something's capacity, like how far something goes into a piece of clay. Clearly, lots of other factors can decide how far something goes into the clay, like how much the clay can stick to the surface of the thing. So you can destroy the function of the friction. So there's lots of ways you can create a system that measures poorly because of the fact that it gives a huge advantage to things going faster versus things going slower, or things that are big versus things that are small.
Using Newton's formulas, Monsieur Voltaire, he then drops a second ball from a higher height, calculated to exactly double the speed of the first ball on it.
So, of course, it can't double the speed, right? So the first thing that you would argue is that, of course, Newton told you you can't double its speed. If you double the height, yes, you can double its speed. But gravity as a functional force isn't really good at speed changes. It's really good at speed staying the same. And the thing that's really going to change is momentum. So the more mass you have, the gravity will be working on your more mass. And so you'll hit the ground a lot harder. So the feather and the hammer fall at the same rate. But the hammer hits the ground with a lot more energy. A lot more. Not a little bit more, a lot more. Hundreds of times more energy.
So, monsieur, care for a little wager? Newton tells us that by doubling the speed of the ball, we will double the distance it travels into the clay.
Right. That's all you're going to get. Okay? That's how momentum works. You're increasing the momentum at the same rate through the whole process of moving through gravity. So if you double the distance, all you're going to get is twice the energy. That's all. No more. That's what'll be tested over and over again by any kind of device that actually tests how much energy something has, like a spring or like a displacement in some fluid. Let's see, there's certain things that are really, like I said, it's just about your test instrument. What are you testing? What are you using to test how much energy it has? And the simple truth is they're doing the test with really bad instruments. And that's all they're doing here.
Leibniz asks us to square that speed. If he is correct, the ball will travel not 2.
Right. So the joke is, right, now they still don't have the right formula, right? They have mv squared. So Leibniz is still wrong because it has mv squared, and they haven't done the 1/2 thing yet, right? So, this is where it all gets silly.
But 4 times as far.
I mean, they're measuring so poorly that whole doubling of the mass, doubling of the energy. They're getting errors so big that they're twice, 100% off. That's how bad the errors are. And they can't even see that.
So, who is correct?
Monsieur, I feel Mr. Newton's reputation dwindling.
So the joke is they call this the classical view when it's not Newton. So these people were already anti-Newton in a sense, right? So Leibniz is making an accusation that Newton is wrong and that energy isn't proportional to mass times velocity. That somehow it's 1/2 the mass. Mass is really small, is importance, and the velocity is squared.
Ever so slightly.
Oh, mon père, Tweed, not succumb to her. There is no earthly reason to ascribe hidden forces to this Dutchman's lead balls.
Well, the ball travels 4 times further.
Right, so this is clay. So it's not really good at telling you exactly giving you proportional results. So this is more about damage. It's not about how well you can damage something, not about how well you're measuring exactly how much energy it has. So a simple example I could give for how this prejudice of speed becomes relevant is just recognizing that, let's see, I should be able to do this, and I can get rid of that, probably. All right, let's be quick. So let's say you had a container, or let's say it is a block of clay, and you're going to do something to it, right? If I move something into it quickly, you could sort of understand that what's going to happen is there really isn't going to be any time for any of the force, okay, the hitting of the clay, and you're starting to move it, and you can't move it very fast because it is clay. So you can imagine it's something harder, this would happen much quicker. And that what's going to happen is that energy is going to hit, and it's going to reflect back. At different points, it's going to reflect back. At different points, it's going to reflect back. At different points, it's going to reflect back. And so those reflections are going to slow down the progress of something moving slowly. So if you move slowly in, you're more likely to feel the pushback. If you move quickly in, there's not enough time for the pushback to do its thing and come back and hit you. So you get much further into the material because there's no pushback. And so that's a simple way of understanding why there'd be a huge prejudice in your measurement. That is, you're measuring how far it goes in and saying that's its energy. Well, it's not really its energy. It's really, you're just measuring the fact that there's a huge prejudice in your device for something that goes slow versus something going fast versus something going slow. And so you can obviously come up with other devices that probably would give a prejudice to the slow-moving thing versus the fast-moving thing. And so all this history is just decided by the fact that they had a prejudice for fast things, so they made a formula saying there's real extra energy. And let's understand, it was called living force. The only thing Young did that was good was he changed living force or living energy, a living fluid thing, into energy. So we'll give him credit for that. But it's really bad physics. It's a really poor way to measure it, and they should have been able to recognize that maybe this tool for measuring is what's the problem. Because if they would have dropped it on springs and saw how far the spring was compressed, they'd see that, oh, it is only a doubling. So springs would have given them the right answer, clay gives them the wrong answer. And, you know, physics hasn't figured this out for 200 years, which is kind of amazing. 250 years.
Anyway, in 1740, Emily du Châtelet published a book called Lessons in Physics, which was the first to champion Newton's theories and the idea of the living force, and helped promote both Newton's and Leibniz's theories in France.
Right, so the living force is what they called this fake extra bit that Newton didn't account for. So, you know, how can you have it both ways? Energy is either mass times velocity, or velocity is everything and mass is nothing. And the simple argument is they could have solved this problem by just putting objects on springs, right? Just push them into a spring, put a heavy thing, put a light thing, you know, and you'll see the light thing goes further. There's no surprise there. Yeah. So, you know, there's no magic to it, but you know how much energy produced the extra motion. The same amount of energy.
France, Germany, and even England. Du Châtelet continued to research science, and in 1747 she completed her magnum opus.
Too bad you never saw it published because she got killed by her baby.
The first and still gold standard French translation of Newton's Principia, with footnotes about the living force.
Voltaire's baby, apparently.
Tragically, she died just before its publication at age 42 from complications from childbirth. After her death, Emily...
And she knew she was going to die, frankly. Pregnancy was not very, very good for her, so she knew she was doomed.
Emily du Châtelet's ideas about Newton, Leibniz, fire, light, philosophy, and living forces were all reproduced, sometimes plagiarized word for word, by her friend Diderot in the very influential French encyclopedia.
All right, this is all kind of useless to this purpose, but you get the message that this got very popular. Lots of the elite people all fell in love with this idea. They all figured out that somehow, because of these experiments, that something was wrong with this basic idea of just mass and velocity, and they took a simple concept and perverted it into mush because they didn't do any controlled experiments. Now, what happened when they did do them eventually, I don't know why they still argue that there's 4 times the energy when it doesn't exist. And it creates a logical paradox where, again, you can just do this stupid train analogy and you're already done. You're already saying, how can they possibly have a different amount of energy when I put them at 2 ends of a tug-of-war rope and they have exactly the same amount of energy? So when I put them right opposing each other, I know they're going to show me that they have exactly the same amount of energy. So how can I have a formula that tells me one has twice as much energy? And like I said, it's not a little bit off. It's completely off. I mean, twice as much energy. It's silly how much it's off.
Her influence was obscured by her death, but her scientific ideas flourished. Fast forward to England in 1807. That was when a doctor and scientist named Thomas Young.
Okay, so this is two-slit fame, right? So here's another point where, Young is famous and he's, all of this great science, but it's completely sloppy science again. So another example of, they didn't do very controlled or very well done experiments. Young's two-slit experiment was sloppy, ugly as you could get. It doesn't really show the whole pattern. It wasn't even in monochromatic light. And then he drew a picture and said, this is what's happening. Well, what he drew wasn't right then, and it's not right now. It doesn't get any part of the pattern right. And the only way you can make it get the right pattern is you have to make the slits so small that you can't even make slits out of them. That is, they have to be less than a wavelength of light. It's very close to just a very small distance, a distance so small that it can't change the pattern. Or you have to make the impediment that small. And that's the only way they can make his drawing work. It doesn't work any other way. Any other slit arrangements, it fails. And it doesn't fail by a little bit. It fails catastrophically.
Was famous for his double slit experiment from a few years earlier that demonstrated that light acts like a wave.
Well, right, again, this acts like and blah, 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 baby talk. He drew an explicit picture that this is what's happening, okay, that the two waves go out and they interfere with each other and you get results. And it's wrong. It didn't work then. It still doesn't work. It's nonsensical. It's not reasonable theory.
Was asked to give a series of lectures on the current state of science. Young decided to make his lectures as simple as possible because he wanted to dedicate it to the women in the audience. Specifically because he felt the upper class women would be better served if they spent their time in the, quote, acquisition of knowledge instead of wasting their time the insipid consumption of superfluous time. Anyway.
Yes, well, whatever. Clearly that would have been, it was nice that some men, appreciated that women were kind of going to waste, because of objectification.
In his 5th lecture out of 60, he decided to rename the living force, or the mass times speed squared, saying...
Okay, the mass times speed squared. So they still haven't figured out that to put the half in front of it. So, which is the funny part, right? So they still haven't figured out how grossly it's off. So it's still off 100%, right? A half is, you're basically saying you're 100% off. You're, twice as much or half as much is, same difference. So they're still 100% off, in their accuracy of saying how much energy is in something. 100% off their own off number. So the numbers... if they don't put the half, now they're 200% off, right? So at least with the half, they're getting a little closer to the truth.
That, quote, the living force is somewhat more concisely expressed by the term energy. His lectures were published as a book.
So momentum is more concisely termed as energy. Momentum is all there is, whether it's in a subatomic particle or whether it's a planet or, a galaxy. All it matters is mass times its collective velocity. That's it. What's the collective mass doing? Add up all the mass and all of the momentum vectors for all the mass, and that'll tell you what your energy is. That's it. That's all you need. It's a simple little vector pointing in a direction. That's it. And you just either have a long vector for a lot of energy, or you have a short vector for a little energy. And that's it. There's nothing squared. Nothing gets squared. Nothing gets halved. And the contribution is both by your mass and your velocity. The mass has to exist for the velocity to mean anything. If you don't have any mass and you have velocity, you have nothing. Okay, nothing does that.
And soon his simplified physics for the ladies caught on in England, and the term energy was used instead of living force, at least in England. Now we go back to France, and two ex-soldiers, Sadi Carnot and Gaspard Gustave Coriolis, who are interested in the efficiency of machines.
This won't help much because this gets into a whole bunch of arguments about heat transfer and all that kind of stuff. We know that has nothing to do with this velocity argument. So that's where it sort of ends. So frankly, the whole thing is mush based on a misunderstanding of what a proper measuring tool is. The clay wasn't a good way to measure the energy of something hitting it. It cheats. It gives fast things advantage over slow things. So it doesn't measure momentum. It doesn't measure energy correctly, evenly. And so because of that bias, they wrote something into reality, a new equation, anti-Newton, un-Newton, where you are squaring a velocity and saying velocity is all that matters to your energy and the mass is half. It's very unimportant. So velocity very important, mass very unimportant. When logically it can't be any other way, then they have to be equal. And every device that creates a consistent source of energy, like a gun, you a certain amount of charge in the gun. If I change the weight of the bullet, I'll get twice. I won't get any squared numbers coming out of the gun. Same thing if I create receivers, and I'm not thinking of a whole bunch of them, but a steel rod, how much it bends, right? The trains hit the steel rod. We notice how much the steel rod is bent. That says how much energy they have. Well, the train going, 12 miles an hour that weighs 1 ton, okay, is going to bend it a certain amount. Well, the train that has twice the mass and half the velocity is going to bend it exactly the same amount. So those real measuring devices tell you the truth, and this formula is just a pile of crap. There is no living force. There's no special energy. There's no thing called a special kinetic energy that doesn't have anything to do with momentum. That's all nonsense. Momentum is everything. It's the whole story. It's the end of the story. All right. And this is huge. I mean, this is a gigantic mistake. And here it is sitting there, right, still in physics. It's still sitting in here, even though anybody who's honest, this has to tell you, of course this is rubbish. It has to be rubbish. You can't, momentum can't be, it can never lie. If two things have the same momentum, they have the same energy. All right. It's just a fact. All right. So let's go back to this other junk. So some asshole left a comment, saying I was wrong, and he deleted it. So I guess he figured out, oh, maybe you're not wrong. But he did a link to this piece of shit video, so I figure it's worth playing just for the lulz, so to speak. But yeah, it's just wrong, and it's just so
in today's video,
obviously
I'm going
wrong.
to go over an explanation of momentum and specifically inelastic collisions. And this is what an inelastic collision is. It's kind of definition of an inelastic collision is a collision where the kinetic energy, the total kinetic energy of the system of, let's say, the two objects is not conserved.
So there's just no way to ever have anything where it's not conserved in the sense that you can follow it. Okay, so it's never destroyed. To say it's not conserved is nonsense. It always goes somewhere. The only argument is whether it stays in the two things you're playing with or whether it goes someplace else.
kinetic energy is not conserved. And that is kind of different.
Energy is always conserved. It's always going somewhere. You can't get rid of the vector. Once you have a momentum vector somewhere in the universe, you have to make it go somewhere. It can't go nowhere.
Differentiation between an inelastic and an elastic collision. In elastic collisions, kinetic energy is conserved, but in inelastic collisions, kinetic energy is not conserved.
All right, so just absolute nonsense. Absolute nonsense. So if you had a perfectly elastic collision, that is the train example, for example, right? If I made the coupler on the train like I made them into like Newtonian steel balls, the trains, and so you have this perfect contact, bang, contact, and all the energy can be transferred through that steel. So I have very little losses. The truth is still the truth. The truth is that there is no deformation. There is no this. There is no excuses for it going in different directions. And, of course, the energy is conserved. And they're just saying it's not doing the same thing the momentum's doing. There's no logic to them saying you can conserve the momentum and yet you can lose kinetic energy. There's no logic to it. There's no place. Where did the kinetic energy come from? How can you you can't have it for free and you can't lose it to nowhere. You have to take it from the momentum.
Some of the energy when the objects collide is converted into vibrational energy of the molecules or heat, or goes into deforming the two objects when they collide.
And that has nothing to do with this idiotic formula, because that will change the momentum. If the interaction means you've created heat, it came out of your momentum. If the interaction means deformation, it came out of your momentum. You can't create any of those things without sacrificing your momentum to create them. So vibrations, heat, deformation, all of that stuff has to be made out of your momentum. It can't be made out of anything else.
So some of the energy is converted into other forms of energy. And that means the final kinetic energy is less than the initial kinetic energy, but the total energy...
So it's just absolute nonsense, right? There's no potential energy in any of these examples. So there's no such thing as a difference between the kinetic energy and the total energy, because there's no potential energy anywhere in the experiments, anywhere in sight. So you can't just make up this silly notion that, well, yes, the kinetic energy is destroyed because it was somehow turned into potential energy, or somehow there was extra potential energy and we didn't cite that before, and that's where the extra kinetic energy came from. You can't use that as an excuse, because none of these experiments have any potential energy in them.
Of the system is conserved. You have to conserve energy, but the kinetic energy is not conserved.
So again, the only way you cannot conserve the kinetic energy is that it actually has to use up the momentum somewhere, has to steal your kinetic energy, the momentum, or it has to get it from some potential and convert that into kinetic. Again, none of these examples have any potential energy in them.
But, of course, momentum is conserved. In all collisions, whether they're elastic or inelastic, momentum is conserved.
It's just impossible for that to happen, and you call it energy. That's what momentum is.
All right. Now, there are two kinds, just a little more detail here, two kinds of inelastic collisions. There's perfectly inelastic and partially inelastic. What's the difference? In a perfectly inelastic collision, the two objects stick together, and in a...
All right, so this stick together thing is just absolute bullshit. So it just doesn't have anything to do with the facts. You can create a circumstance like the train example where they stick together, but they're not sticking together for any other reason than you've locked them together. But there's nothing sticky about the circumstance. You could have the circumstance be that they just cut their velocities in half. The thing going a certain 20 miles an hour hits something, and now they're both going 10 miles an hour. And it has nothing to do with stickiness. They could be 5 feet apart from each other. The point is you now have twice as much mass moving in the direction. It doesn't matter whether the mass sticks to each other or not.
Partially inelastic collision, the two objects do not stick together. Now, here's kind of the typical perfectly inelastic collision. This is the ballistic pendulum. We take a bullet, we shoot it into an object, it embeds in the object, and that object swings up like that. Now, those two objects stick together,
So again, pendulum's not a great way to measure something either. I suppose it's as good as a spring in sense you're working against gravity. So if they had done this with the clay experiment, it would have been a much better way to test, because at least you have a consistent spring you're pushing up against. But the simple truth is, if I double the mass of the bullet and at the same velocity, this will not travel 4 times higher. You know.
That is an example.
Well, it's the other way around. If I have the mass of the bullet, geez, there's no way of getting around this. This won't go any further. The gun fires with a certain amount of energy. The energy goes into the projectile goes into the object at the end. It's always the same. There's no other kinetic energy. By reducing the mass of the bullet and making it go faster, I'm not going to make that pendulum go higher.
Of a perfectly inelastic collision. Now, for a collision that is partially inelastic, you can think of this here as a basketball. The basketball is bouncing off the ground. You'll notice it doesn't bounce back up to the same height because some of the energy of the ball, the kinetic energy of the ball, is lost when it strikes the floor, because it goes into deforming the shape of the ball or into vibrating the molecules in the floor. But the two objects do not stick together. So there's perfectly inelastic and partially inelastic based on whether or not they stick together. In a perfectly inelastic,
whether they absorb all the energy stays in the system is always really saying. Is all the energy going to stay in the objects you're measuring, or is some of the energy going to leak out? That's all.
collision, that's when we have the maximum amount of kinetic energy, mostly due to the fact that the objects are bonding together and there's deformation and changing of shape. In a partially inelastic...
So again, there's more nonsense about all this stuff that didn't happen in these thought experiments. Just remember, you can't have the same momentum and have any losses at all. You can't have lost any heat, energy, any kind of energy at all and have the same momentum. Impossible to do that.
Collisions when the two objects do not stick together. Now that is probably the most common form of collisions that we see in our everyday life. Okay, but there are two possibilities, whether it's perfectly or partially inelastic.
I'm sorry. I just wanted to get to this. This is the part that's just funny. So I just,
Okay, now what I want to do is I want to kind of prove to you how the kinetic energy is not conserved, and in this case we're going to do first how the, kinetic energy is not conserved and the momentum is conserved.
So this is just so bad. You're just saying, how can somebody as a physics teacher do something this bad? It's just so bad.
Okay, so we have two objects, M1 and M2, and they have the same mass. M1 and M2 are equal to each other. M1 is equal to M2, and they have the same speed, but they're traveling in the opposite direction. So the speed of their velocity is the same, but the direction is opposite. So V1 initial, the speed is equal to V2 initial, but they're traveling in the opposite direction. Now let's kind of conceptually or qualitatively add up their momentum and their kinetic energy. Well, the first object, M1, when we multiply the mass and the velocity, we get a positive velocity momentum.
So why didn't he use the kinetic energy formula? Why is he using a momentum formula? Anyway, it doesn't matter. But
initial and momentum for number one, and when we add or multiply, but when we multiply the velocity and the mass in number two, we get a negative.
All right, there's no such thing as negative momentum. So right there, it's just silly. It's always a positive vector. You can't have inverted momentum. Okay, there's no inverted momentum.
Momentum for number two. Now, momentum is a vector.
So it's just idiotic to do this. It doesn't happen in reality. So even if two things have vectors that are pointing towards each other and look like they're going to cancel, they never cancel. Okay, they don't just slide into each other and all the momentum just goes away. It has to go in these other directions. It doesn't have any choice. It has to go through. It has to smash by. It has to do something. It'll fly off at all kinds of angles. The momentum can never, ever, 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 ever just go away. All right? You can't eat the other momentum. They can't eat each other. The momentum has to crush. It has to deform. It has to go somewhere. So this was just so deceptive to say I could just put a minus sign on one of those momentums because they're in opposite direction. You can't just put a minus sign on one of them. They're both positive momentums. It's almost the perfect circumstance in that sense. Well, just because you have the velocities. Either one of them is going twice as fast and one of them's not moving, right, in real space. It could be that one of them's moving twice as fast as the other. technically. Technically one of them could be standing still in the universe, the other one's moving twice as fast. And obviously the momentum would be exactly the same. So obviously the momentum is something they both have, and it's obviously a positive vector.
Have a direction and a magnitude. The magnitude of the momentum is the same, but the directions are opposite to each other, so when we add them up, the total momentum of that system of M1 and M2 is equal to 0.
So it's just idiotic. It won't equal 0. It doesn't equal 0 when they're moving. It doesn't equal 0 when they hit each other. It'll never equal 0, okay, because there'll be a whole bunch of stuff flying off in all kinds of directions when they hit each other, or else they'll reverse direction and have complete momentum in the opposite direction. And when they're going in opposite directions, is he going to say they have opposite momentum again somehow? Somehow this is the negative one and this he'll call positive? I mean, it's just arbitrary nonsense.
The total. But they are moving and they have some kinetic energy. Kinetic energy is not a vector. Kinetic energy is a scalar. So they have the same kinetic energy. And we add them together, we get that they have like 2 KE. Okay, so they really...
So somehow, yes. So when you add them together, you have 2 KE, but your KE is made out of a formula that doesn't give you the right energy. So you have a number that's totally wrong because you've exaggerated how important velocity is.
That system has no momentum, no total momentum, but it does have some kinetic energy. All right, now,
see, as it stands, they both have twice as much energy as they really have by one formula. One formula says they have twice as much energy because they have a positive velocity. So any velocity means you've already corrupted them in the sense they have twice as much energy as they really have because you're measuring their velocity, you're squaring it. Big mistake.
After the collision, those two objects have the same mass, we're traveling at the same speed in opposite directions, so when they strike each other, it's an inelastic collision. They're going to stick together and they're just going to stop right there in the middle and they're going to...
All right, so we know that doesn't happen. They're not going to stop right there in the middle. All kinds of deformations going to happen. They're going to explode into pieces. Little red bits will fly over, little blue bits will fly over. All kinds of shit is going to happen. There's no way it just stops and they all say, there, we're done with that. The energy has been destroyed. No, the energy will find all kinds of new paths to take, and we'll be flying all through those new paths. So it's just absolute nonsense.
Not move anymore. And that means that the initial velocity, not the initial velocity, but now the velocity of number 1 is 0, and also the velocity of number 2 is 0.
So if they were hard objects, obviously what's going to happen is they both have positive momentums in these opposite directions, and it just make a complete nonsense out of this silly, idiotic 0. Hey, look, they started with 0 momentum. And look, they have 0 momentum. I mean, it's just such a lie.
And once again, we're going to calculate, so to speak, qualitatively the momentum of each one. The momentum now, the final momentum of number 1 is 0 because it's not moving. And the final momentum of number 2, of object number 2, mass number 2, is also 0. So when we add them up, the two momentums, this is 0 and this is 0, and 0 plus 0 is that, rats, right? You guessed it, that the total momentum of the system is still 0.
So we know the system is going to be all the little bits that are moving in all kinds of directions. So again, it just makes no sense. It's so bad.
Kilogram meters per second. Okay, so that means that
you
can see when we went from before to after the collision, that the momentum was conserved. But what about the kinetic energy? Well, they're not moving. Now, here they were moving, so they had some kinetic energy. Now they're not moving, so the kinetic energy number 1 is 0, and the kinetic energy of number 2 is 0. And when you add those up again, once again, 0 plus 0 is still 0. And now the system has no kinetic energy. You see, we went from some kinetic energy to no kinetic energy, so we did not conserve kinetic energy.
So it's just idiotic because we know the kinetic energy, we can understand that as having a vector too. There's no question that the kinetic energy is in a direction. So why didn't he just make that plus kinetic energy and minus kinetic energy? If he can make negative momentum, right, or unmomentum, or anti-momentum, why can't he just make anti-kinetic energy the same way? I mean, it's just such just playing. This is just such a nonsense. I mean, this is just it's not even a trick of math. It's beneath that. This isn't even a math trick. This is so obvious.
And I think that's kind of the best, maybe the easiest, most simplest, kind of straightforward way to show you that in that kind of mathematical way without doing much calculation.
Yeah, without making any sense at all. I'll just arbitrarily, erroneously put minus signs to make everything work out. I mean, just terrible, awful.
To show you that momentum is conserved, 0 and 0, but the kinetic energy is not conserved. We have some kinetic energy, and here we have no kinetic energy. All right, now we're going to now talk a little bit about the kind of a simple equation, or the kind of how we derive the equation for the most common form of an inelastic collision. And the most common example you'll see, the kind of very simple way we start is we have one object that's moving with some initial velocity, and we have another object, and they're going to collide into each other because M2 is not moving. Now they're going to stick together because it's an inelastic collision, and that means they're going to be stick together like...
So now we're back at the train, so this is going to be more applicable to the argument. And you'll, well, it just gets, like I said, the whole thing is quite hilarious.
M1 and M2 stick together, and they're going to be moving off with some final velocity, and the velocity of both those objects is the same because they're stuck together like one object. Now they have one velocity. So an object...
yeah, and they have one vector of momentum, and this is realistic. Just look at the arrow. The arrow is the momentum. You have 0 momentum plus
object that's not moving, and
plus an arrow of a certain length, and then afterwards we're assuming no losses, and so we have the same momentum arrow, and now we have twice the mass. And so we know the final velocity is half. That's Newton. It works perfectly. It's a perfectly sensible way to understand the transfer of energy. You should be done. The whole thing is done right here. It's all over. It's done. You don't need anything else. This is all the physics you need. You don't need any other physics because any other physics won't be anything rational. You can't add anything to it because it's perfectly explained. You either the mass and the velocity make equal contributions to the energy the thing has, and that's it. You can add more mass, you can add more velocity. It's always equal. You can have more of one and less of the other, and it always comes out the same. Then take away mass blocks, you have more velocity. Take away velocity blocks, the mass is more, not more. It's the number. Your final number is the total number of blocks, period.
Then they move off together, and we're going to show you that, well, we know now that momentum is conserved, so we're going to use our conservation of momentum and our momentum equation. The momentum is the mass times the velocity, and we're going to sum up the momentum before the collision, and that would be the mass of 1 times the initial velocity of 1, because momentum is mass times velocity, plus the mass of 2 times the initial velocity of number 2. That's
energy is momentum. So energy is the same thing by the description of it. Kinetic energy is described as the energy it takes to make something move, and it's the energy it takes to stop the thing from moving. It's exactly the same as momentum. There's no difference. P equals E equals mv. Momentum is energy, always, everywhere, in all cases.
The momentum, the total momentum before the collision, because we have conservation of momentum, we can set that equal to the final momentum after the collision. Now you see I have m1 plus m2 times the final velocity. Now those two objects are now stuck together, so we have the total mass and a single velocity. Okay. Now the most common thing you're going to be asked to find, or kind of the simplest, maybe the first thing you'll usually be asked to find, is what is the final velocity after the collision. You'll be given the two masses. You'll be given this velocity, you know the two masses still, and now you want to know what's the velocity when they move off together. So now we're just going to solve.
I mean, it can't be a simpler equation. It really can't. It's so simple. It's so obvious that, if I have twice the mass, now I have to have half the velocity. If I had twice the velocity, I have to have half the mass to get it, the same amount of energy. The same amount of energy can only create completely inverted MV numbers. If one's 3 and one's 2, then I have to make 1 2 and 1 3. I mean, always have to use the same thing. It always has to come out to 5. Anyway.
For the final velocity, we're going to solve for the final velocity by dividing by m1 plus m2. So that means that m1 times v1 initial plus m2 times v2 initial, that's simply this term over here, divided by the sum of the two masses is equal to the final velocity. Now, this is kind of an overall equation, kind of a general equation we can use to find the final velocity. If, like in this case, we have one object, the second object...
You could just set up a proportional relationship and obviously just cross-multiply and you're done, but whatever.
Object is not moving. That means that this term is going to be 0 because the initial velocity number 2 is 0, 0 times the mass is 0, and that means if we have a situation where one of the objects is not moving, then this is kind of the general equation that we can use. Okay, this equation and this equation are kind of the same equation. We just eliminate this term because V2 is at rest before the collision. And then it's a little bit interesting to see I can pull this term out, the velocity initial of number 1, and you can see that the final velocity is really the ratio of the mass of number 1 divided by the sum of the two masses times the initial velocity of number 1. Okay, so this equation is really good for whether both objects are moving or not. This equation we can use when one object is not moving, and this is kind of just a little bit more.
Yeah, well, whatever. All you have to find out is how much did you change one of the numbers, and the other one has to change in the reciprocal manner. Period. Done.
For generalization of that same equation. Okay, so now we're going to talk a little bit about kinetic energy, how kinetic energy is not conserved.
Okay, so let's understand this is a completely silly formula. It has nothing to do with reality. The right formula is kinetic energy equals mv. There's no squared and there's no half. So let's understand the history, right? That the history was they thought it was mv squared for a long time. Young's time, they were arguing it was mv squared. They didn't even know they were supposed to put a half in front of it. That's how far off this has always been. This is how far off they were. I mean, this is 100% magnitude. I mean, if it's 100 joules, they thought it was 300 joules. You know, and this v squared went endlessly, right? Without even this half, this v squared just ended up being an endless exponent where you could theoretically keep making more and more energy by just making something go faster and faster. So just carving its mass off and giving it higher velocity, you could somehow make it more and more, have more and more some kind of real energy. It can't have any more real energy. Again, the momentum of the bullet, you know, is the same as the momentum of the bowling ball.
This is a little interesting thing to do about how we can figure out the final kinetic energy and the change in the kinetic energy. So what I'm going to do in this case is I'm going to look at the ratio of the final kinetic energy to the initial kinetic energy. And I'm going to do that, and I'm going to take that kinetic energy initial. Now we have the same situation. One was moving, one was not moving. Now the initial kinetic energy, this object has no kinetic energy because it wasn't moving. This object is moving, so its kinetic energy is 1/2 m1 v1 initial squared, because kinetic energy is 1/2 mv squared.
So why is he making this huge mess out of this, right? You're just comparing how much velocity to mass you have here and here. So why not just do the equation here and then do the equation here? What's so complicated? You're not comparing m1 and m2. You're comparing m1 to m1 plus m2 with the slower velocity. So you're just making a simple comparison. So what's the kinetic energy of v1? The object going 12 miles an hour that weighs 1 ton. And then you're just saying, here's the other object going 6 miles an hour, weighs 2 tons. That's it. And if you do the formula, this one ends up having twice as much energy as this one. If you pushed them with springs, that wouldn't be your answer. If you caught them with springs, that wouldn't be your answer. They would both compress the spring the exact same amount. So how can they have two different amounts of energy? Obviously they can't. So the formula is garbage.
Okay, now the final kinetic energy looks a little bit...
It's based on a misunderstanding, because they caught, instead of catching trains with springs that gave them the right answer, they caught trains with clay that gave them the wrong answer.
Bit more tricky, but it's not really that hard. We have 1/2 again. Now this is the mass because it's the sum of both masses, so it's m1 plus m2 because they move off together. So this object really has a mass of m1 plus m2, and then its velocity. Okay, now this is the term we had from the previous slide this is the equation we used to calculate the final velocity. Okay, and it's velocity squared. So I had to take the velocity, the final velocity, and I have to square it. Okay, so now,
so why is he doing this nonsense, right? We don't need any of this. We know what its final velocity is already. But anyway.
Now we're going to eliminate a bunch of stuff. This equation looks a little nasty. It's actually not that bad, but it looks a little nasty. But we can eliminate a bunch of stuff, and we'll see what comes out. I think it's kind of interesting.
Yeah, no, it's not
interesting. You can
interesting.
see now we have
I'll jump ahead. There's just no
here.
point.
Here we have m1 plus m2 squared. The ratio of those two kinetic energies is simply m1.
So now we'll find out. Right. Now he's cutting to the chase, which is somehow the mass is going to be irrelevant and the velocity is the only thing that matters. Or inversely, we're just going to sit there and cut the mass in half.
divided by
a commercial.
M1 plus M2. And really what that is.
So this guy has 130,000 subscribers. I guess, who knows how. The video only has, 8,000 views. But, yeah, maybe we can push him into playing my video.
That's the percentage of the remaining kinetic energy, the kinetic energy that remains after the collision, because that's what the ratio kind of is. It gives you the comet cell, gives you the decimal, less than 1, multiplied by 100, you get the percentage of the kinetic energy that remains.
So he did this formula in this bizarre way where he canceled out all the velocities just to say we're just going to multiply the mass into the other single mass. So obviously it's the same thing as cutting it in half. So he's saying there's half as much kinetic energy, but he isn't getting the answer for how much kinetic energy. He's lost the joules thing here. We don't have any joules per second thingy. We don't have any velocity left in the equation, so he can't possibly answer the question in terms of how many joules of energy there are. And he's just using this silly argument that somehow this big thing going slower has half as much energy as the small thing going faster.
Remains after the collision. You can figure out the percentage if you know the initial kinetic energy, the percentage, you multiply that, and you can find out the percentage of how much kinetic energy is remaining after the collision simply by taking M1 and dividing it by the ratio of M1 plus M2. And you notice this is going to be bigger than this.
It's obviously going to be twice as big by the definition of this experiment. So yes, it's going to be twice as big. Damn.
So that means that kinetic energy is lost in that collision when we take the ratio like that.
All right, so somehow he's saying there was kinetic energy lost. Now, there was no place for it to be lost because the momentum stayed the same. So again, the argument is so simple. You can't lose energy if your momentum stays the same. Momentum is a vector. It's a real piece of energy. You can't just make it go away. So how did you lose half of your momentum vector and not lose half of your momentum vector? Where did it go? If it went somewhere, where did it go, and how does it still stuck there? How does the momentum still exist if it lost energy? It's not possible.
Okay, so therefore, I think that's everything we wanted to do. I kind of went over a definition of inelastic collisions. We talked about kind of how we prove, or a little case where we can prove that the momentum is conserving kinetic energy.
Now, some crank in my comments says something about doing the experiment or something. I mean, this is such a simple and basic experiment. It has been done over and over again. I mean, I could show you, Professor Lewin and the little air carts and different other kinds of things. Everybody should know this stuff. So I'm not saying anything that isn't already in 4 million experiments. I mean, there's just no way to not understand this simple principle. And all that's being argued here is, can anybody ever prove that faster object has twice as much energy as that slower object? And they'll never be able to demonstrate it. They'll never be able to show it with any test instrument that has 4 times more energy.
We did some equations. We talked about kinetic energy and the momentum for inelastic collisions. So thank you very much for watching. I hope I helped. If you did, please roll.
So again, every test instrument you could invent, tying strings to the train and then running over a pulley and lifting a weight, all kinds of ways you could test how much energy the train has, okay? And all of the ones that are rational tests, that is, don't have something to do with how far it flies off a cliff, will show you, okay, that they have the same amount of energy. You can't say one has twice as much energy and be reasonable, because it can't be possible. The forces that created them can be exactly the same. I can compress a spring. I put the twice as heavy train on the spring, it goes 6 miles an hour. I put the other one on the spring, it goes 12 miles an hour. That's how much energy. It was the same amount of energy. They have to have the same amount of momentum. They still have to have the same amount of energy. There's no other place for them to get any extra energy. There's no way the one going 12 miles an hour can have twice as much energy. It can't. There's nowhere for it to get it from. All right. So this is just glaringly stupid. So you're just saying every time they use this formula, it was a half-baked idea, okay? Like I said, the history of it was shown. It was half-baked, based on penetrating clay. So it was a less than perfect experiment. Half-baked idea that there's any need for this extra living energy thing to ever be even understood as a thing that exists. There's no living energy. There's no extra energy. There is, in fact, velocity sometimes comes with advantages. Okay, you can cheat with velocity. You can evade friction. You can evade lots of the counter forces to your penetration of something or your destruction of something if you're going fast enough. It has nothing to do with how much energy it has. And so this whole thing is just a big, juicy, fat lie. There's no extra joules of energy. So again, they talk and say, oh yeah, we can calculate 1/1,000,000th of a bazillionth percentage of how heavy an electron is. Well, if you're using this formula, you're not getting the right answer, because it has nothing to do with anything called real energy. It's fairy energy, figment energy. This is just complete nonsense. I just can't believe physics is this. I didn't know their mistakes were this obvious. I mean, fuck. This isn't subtle at all. This isn't just subtly stupid. This is profoundly and overtly stupid. And you could see it in the physics girl, video. She's sitting there saying right to your face, well, here, it didn't lose any momentum, so it's a pretty clean exchange, right? And nothing was lost. Okay, all I do is reduce the velocity, and I doubled the mass, and so nothing was lost. A perfectly clean experiment. And then she talks about how half the energy is lost, and there was all kinds of heat, and there was all kinds of sounds, and there were all kinds of ways it lost all its energy. I mean, that's how you turn them into babbling idiots with this nonsense. It's such a stupid equation. Well, okay. That's got to be enough. I shouldn't have to beat this horse. But all these people would just say it's okay. Leave it broken. We don't care. We're not going to fix anything. We're not going to, it's just amazingly bad. That you're all so fucking, you're stupid and you're so dishonest. You just don't understand how, yes, I can see they just made a huge mistake. A bunch of silly people with wigs on made some mistakes, and they put something dopey in physics that should have never been there. And we all just bought it, and we all just accepted it, even though, because nobody really just sat there and said, this doesn't make any sense. What was wrong with Newton's idea? Mass and velocity equals energy. What was wrong with that? Oh yeah, there's nothing wrong with that. It's the right answer. You're done. And they blew it. They screwed it up. I don't even know how else to argue this. I mean, do I really have to demonstrate? Do I really have to sit here and find some ball bearings and little springs and just show you how it can't be more energy? It's impossible for them to have a different amount of energy. It's impossible for two things to have the same momentum and have a different amount of energy. Shit. Just saying this. Well, whatever. The stupidity runs deep with you people. You are strong with the force of stupidity. Regular Judies. Anyway, till the next time and stuff. Such. Yeah. And I shall return or